our channel Knowledge Hub. Friends, subscribe to our channel and click the bell icon for the latest update. Today we're going to start with your chemistry of class 12, and this is your class 14 that we had completed your class 13 as well. And so first of all, it's a huge request from my side to all the viewers to please go through with the subscribe button and please like, share and subscribe our channel so that many and maximum people can get the information at once, and even though you can also enjoy the video as well. On the same behalf of it, we'll start discussing about unit 5, which is your surface chemistry. And before that, we had completed your unit 1, unit 2, unit 3 and unit 4 as well. Unit 5, which we had started, and hopefully if it is not exceeded, we'll complete that soon here. And first of all, it's a huge request from my side before starting with it. A huge request from my side to all the viewers to please go through with the subscribe button and please like, share and subscribe our channel so that many and maximum people can get the information at once, and even though you can also enjoy the video as well. So here we'll discuss, first of all we'll discuss the adsorptions of reacting molecules and formation of intermediate and desorptions of a product as well. And then after that we'll discuss about many more things in terms of it, like enzymes, catalysts, and as well as activity, selectivity, shape selectivity catalyst of the zeolites that we have discussed here. But before starting with this, we have to discuss the adsorptions of reacting here. So on the same cases, with the same here, that is we have a structures that is to be as follows. So this is what we have here. Okay, so this is your catalyst surface having a free valency. Catalyst surface having free valencies, that is plus A and plus B. It will give, this is adsorption of reacting molecules, will give that we have, which is A in terms of it, B we have. So with the same cases here, that is your that is adsorption of reacting molecules. Here, so here we have A, that we have, this is B here, these were connected, so this is an intermediate. Then after that, this is desorption of product molecule, which is your B minus A plus, this is your product, and it will be, that we have this is catalyst. We'll go ahead and that we have to talk about it. So even in the small quantities, and it however does not explain the action, the catalyst, and that is promoters and catalytic poisons as well. So we'll discuss important features of solid catalyst. Important features solid catalyst here. So this is the first for that we have is your activity. In terms of activity, where that is the activity of the catalyst that depends upon the strength of chemical options to a large extent, and that the reactants must get absorbed reasonably strong on the catalyst to become active, and however they must not get absorbed so strongly that they are abolished, and reactants are left with no space on the catalyst surfaces. Catalytic activity increases from the group 55 to group 11 metals, with the maximum activity that being shown by the group 7 to 9 elements of the periodic table here. So for that we have the reaction. We have 2H2 plus O2 will give 2H2O, that is in the form of liquid here. Another we have is your, that is selectivity. In terms of selectivity here, which is that the selectivity of the catalyst is its ability to direct a reaction to yield a particular product. For example, starting with the H2 and CO, and using the different catalysts we get the different product as well, and that we will be forming it in the form of CO gases plus 3H2 gas will give Ni, which is CH4 gas plus H2O gas. Another we have is CO gas plus 2H2 gas. It will give CuZnO minus Cr2O till CH3, sorry CH3OH, that is we have. Another we can say that here is CO gas plus H2 gas, that it will give, in the presence of CO it is HCHO, which is in the form of gas here. So here thus it can be inferred from the absence of catalyst is highly selective in nature, and that is a given substance that can act as a catalyst only in the particular reaction and not for all the reaction here. It means that a substance which act as catalyst here in one reaction may fail to catalyze the another reaction as well, and on the same cases we'll discuss the another topic here that we have to discuss as well, which is your the shape selective catalyst by the zeolites. Shape selective catalyst by zeolites. So in this shape selective catalyst for the zeolites here, the catalytic reaction that depends upon the pore structures of the catalyst and the size of the reactant and the product molecule is called the shape selective catalyst. Zeolites are good shape selective catalysts because of their honeycomb like structures, and they are microporous, that is alumino silicates with a 3 dimensions networks of that silicates, in which some silicon atoms are replaced by aluminium atom, that giving ALOSI framework, and that the reaction taking place in zeolites that depends upon that is the size and the shape of the reactant and the product molecule, as well as upon the pores and cavities of the zeolites, and they are found in nature as well as synthesized for the catalytic selectivity as well. In terms of zeolites, the zeolites are being very widely used as catalysts in that is your petrochemical, which is your like that we have industries for cracking of hydrocarbons and isomerizations, and important zeolite catalysts that used in the petroleum industry like ZSM, that is zeolite sieve of molecular 5, that it converts the alcohol directly into the gasoline, which is petrol, by dehydrating them to give the mixtures of hydrocarbons as well. Now we'll discuss more about related to the another topic that we'll discuss about enzyme catalyst as well, and that we have as follows. cases we'll have to go ahead, and as I told you, with the reference towards the shape selectivity catalyst that we have to discuss by the zeolites here, on the same behalf of it we have to continue with it. And on the same cases here, that the catalytic reaction that depends upon the pore structures of the catalyst and the size of the reactant and product molecule, that is called the shape selective that selective catalyst as well. On the same cases here, that is that zeolites are the good shape selective catalysts because of their honeycomb like structures, and they are a microporous as well, that we had talked about it in the in terms of zeolites as well, where that is your there are microporous that is aluminosilicates with a three-dimensional network of silicates in which some silicon atoms are replaced by aluminum atoms, and that gives ALOSI framework, where the reactions taking place in zeolite that depends upon the size and the shape of the reactant and the product molecule, as well as that is upon the pores and the cavities of the zeolites. They are found in nature as well as synthesized for the catalytic selectivity as well. Zeolites are being very widely used as catalysts in the petrochemical industries for cracking of hydrocarbons in isomerization. That is an important zeolite catalyst that is using in the petroleum industry in ZSM5, and it converts alcohol directly into the gasoline, petrol, that what even I have told you about it. And on the same case for the dehydration, them that to mixtures of the hydrocarbon, where zeolite sites of molecules are the porosity, and that is an SM, and that is represented by 5 here. For the another one we'll talk about it, which is in terms of it only, and that is another is your enzyme catalyst. So enzyme catalysts that we have to talk about it, which is also an important one. So enzyme catalysts, where enzymes are complex nitrogenous organic compound which are produced by living plants and animals. There are actually the protein molecules of high molecular masses and from a colloidal solution in water, and they are very effective catalysts, and catalysts numerous reactions, especially those connected with the natural processes, numerous reactions that occurs in the bodies of animal and plant, that to maintain the life process and are catalyzed by the enzyme, where in the same cases we can say that the enzymes are thus termed as biochemical catalysts, and the phenomena is known as biochemical catalysis. Many enzymes have been obtained in a pure crystalline state from living cells, and however the first enzyme was synthesized in the laboratory in 1969, where the following are some of the important examples of enzyme catalyst reaction. The first we'll discuss about it, which is the inversions of cane sugar, and inversions of cane sugar we'll talk about it. So the first we'll talk about it is the inversion of cane sugar. In terms of inversions of cane sugar here, with the same case, that the inversions of enzyme that converts the cane sugar into glucose and fructose. So for that we have a reaction here, C12H22O11, which is in aqueous, plus H2O, that is in liquid. It will give, that is invertase, which is C6H12O6, which is in aqueous, plus that is your C6H12O6, which is in aqueous. So this is glucose, this is fructose, and this is your cane sugar we have. Okay, so on the same cases, the second we have is your, that is the conversion of glucose into ethyl alcohol. Conversion of glucose into ethyl alcohol. that we have to talk about it. So here, that is the zymase enzyme that convert glucose into the ethyl alcohol and carbon dioxide, and for that we have a reaction for this as well, that is your C6H12O6, which is an aqueous, that is your zymase, 2P2H5OH aqueous plus 2CO2 gases, and which is your ethyl alcohol. This is your glucose. Now we'll talk about the third one, which is the conversion of starch into maltose. Conversion of starch into maltose, that we have to talk about it. So the conversion of starch into maltose, we have 2C6H10O11 O5, that is of 4 power n. We have aqueous plus H2O, that is in liquid. In the presence of that is your diastase, it will give you NC12H22O11. This is in aqueous. So this is your starch and this is your maltose that we have, which is a sugar disaccharides. Okay, now we'll go ahead with the fourth one that we discussed here, which is the conversion of maltose into glucose. Conversion of maltose into sugar, maltose into glucose. Okay, that we have to convert here. So maltose into glucose, that we have to go ahead for the same sake we will be having, and that even though we have to find out as well. So for the same sake, we have C12H22O11 aqueous plus H2O liquid. It will give in the presence of maltose 2C6H12O6 aqueous. This is maltose, and this is in the form is of glucose. Now we'll talk about the fifth one, which we have to talk about it, and that is also an important one. That is the decompositions of urea into ammonia and carbon dioxide. Decomposition of urea into ammonia and carbon dioxide. So there, that the enzymes urea, that urease, that the catalyst is this decomposition that we have to talk about it, and on the same basis, where we have here is your NH2 CONH2, it is in aqueous plus H2O liquid. It will urease, and it will give you a 2NH3 gas plus CO2 gas here that we have. Now we'll talk about the sixth one that we have to talk about it in terms of it, and that is also an important one here. And the sixth one is in stomach, that the pepsin enzyme converts protein into the peptides, while in intestine, that the pancreatic trypsin converts protein into the amino acid by the hydrolysis as well. The seventh we'll talk about it. So there, that the conversions of milk into the curd, and it is the enzyme reacting the brought about the lactobacter, that bacillary enzyme that is present in the curd as well. So here We will discuss the invertase enzymes, the sources, the enzymatic reaction that we'll have to discuss here, that we talk about it here in the detail, even though which is important as well, and you have to know about it and you have to consider about it as well. So we'll make a sort of a table that we have to discuss here in the detail. So let's go ahead for that. That for the same case we'll have go ahead, and that is your enzyme source and enzymatic reaction, that we have to talk about it, and eventually that is important. So in terms of enzymes, sources, and for the enzymatic reaction. So the first enzyme we have here, which we talk about it, which is your invertase. Source is yeast, and the enzymatic reaction we have is your sucrose. It will give glucose and fructose. Second, we have enzyme is your zymase. Source is yeast, glucose. It will give ethyl alcohol and carbon that is your dioxide. Next is your diastase. Source is malt, then it is your starch. It will give maltose. The another is your maltose. This source is yeast, and it is from maltose. It will give glucose. Another we have is your urease. This is soya bean, and here it is urea, that will give ammonia and carbon dioxide. Here it is pepsin. The source is stomach, and it will give you, here is your protein, give amino acids. Okay, that it will give you, and that we have to easily find it out as well. So on the same cases, this is a sort of a table that we have to discuss in terms of some enzymatic reactions that we talk about it. That is another, we'll talk about the characteristics of enzyme catalyst. Characteristics of enzyme catalysis, that we have to talk about it. On the same case, the enzyme catalyst is unique, and its efficiency and high degree of the specificity we have. The following characteristics are exhibited by the enzyme catalysis. The first is most highly efficient. Most highly efficient here, where one molecule of one enzyme that may transforms 1 million molecule of the reactant per minute. The second we have here is that is the highly specific nature. In terms of highly specific nature here, that each enzyme is specific for a given reaction, that is one catalyst cannot catalyzes more than one reaction. An example that the enzyme urease catalyzes the hydrolysis of urea, that is urea only, and it does not catalyzes the hydrolysis of any other amide as well. The third we have here, which is your that is your highly active under optimum temperature. Highly active under optimum temperature. Yeah, so here in the same cases for this, which is that the rate of an enzyme reaction that becomes maximum at a definite temperature, that called that optimum temperature. So on either side of the optimum temperature, the enzyme's activity decreases, and that the optimum temperature that ranges for the enzymatic activities is 298 till 310 Kelvin. Human body temperatures that being 310 Kelvin is suited for enzyme catalysis reactions as well. Now we'll talk about the fourth one which we have, and that is that is the highly active under optimum pH. Highly active under optimum pH. So highly active under optimum pH, that the rate of an enzyme called catalysis reaction is maximum at a particular pH, that called optimum pH, and which is between pH value of 5 to 7 here. We'll talk about the fifth one which we have is your increasing activity in presence of activators and coenzymes. Increasing activity in presence of activators and coenzymes. In the same case, there the enzymatic activity is increased in the presence of certain substance known as coenzymes, and it has been observed that when a small non-protein, which is vitamin, is present along with the enzymes, that our catalytic activity is enhanced considerably. Where activators are generally the metal ions such as Na+, Mn2+, CO2+, Cu2+, etc. So these metal ions, when weakly bonded to enzymes molecule, increases their catalytic activity, and amylase in presence of sodium chloride, that is Na+ ions, are catalytically very active here. The next we have is the sixth one, which we have as follows: influence of inhibitors and poisons. Influence of inhibitors and poisons. So inhibitors of that is your influence of inhibitors and poisons, like ordinarily catalysis, the enzymes are also inhibited or poisoned by the presence of certain substances, and that inhibitors or the poisons interact with the active functional group that we have on the surfaces enzymes, and often reduced or completely destroy the catalytic activity of the enzyme, and the use of the many drugs is related to their actions and enzymes inhibitor in the body as well. Now we'll talk about the mechanism of enzyme catalyst as well, and that even though which is important, and that we have to go ahead further to mechanism of enzyme catalyst. That we have to talk about it. In the same cases, there are number of cavities that is present on the surface of the colloidal particles of enzymes, and these cavities are of the characteristic shapes and poses are grouped or such that NH2 that is CO or OH and SH OH etc. They are actually the active centers on the surfaces of enzymes particles, and that the molecules of the reactant, that the substrate we will be having, and even though which will draw it as well. And on the same cases, for that the molecules of the reactants that we have, that is a substrate which have your completely shape, a complementary shape that fits into their cavity just like as a key fit and into a lock. And on account that the presence of the active groups and activated complex that we have, the activated complex is formed, which then decomposes to yield the products as well. So thus the enzyme catalysis reaction that can be considered to processed into the two steps. So first we'll draw it, and then after that I will be telling you about it. So here first we have is your this we have this is your active, we'll talk about the enzyme catalyst, that is your catalyst. Then we have that we have S, this is E. It will give that we have this is E and this is L. They are combining, then it will give you this is your here this is P. So here this is your enzyme catalyst. This is active state. This is your substrate, which is your reactant that we have on the same cases. And here this is your ENS, as I told you. This is enzyme substrate. With complex. This is enzyme and this is product we'll get. Okay, we'll add in on too. So this represent here, and this is the mechanism of enzyme catalyst reaction, even though we can just represent by the equations here as well. That is your E plus S, it will be E minus S, and then it will be E plus P that we have will get here. We'll go ahead here, and that is for the step 1, that is binding of enzyme. Step 1, that binding of enzyme to the substrate to form the activated complex will be having E plus S. It will give ES that we have. And for the step 2, it will be ES that we have. It will be E plus P that we have here. So now we'll talk about the catalyst in industry, and that is also an important one. So the catalyst in industry, which is important as I told you, and that we have to consider about it as well. So that is your catalyst in industry. So catalysts in industry, we have to talk about it. We have some of the important technical catalytic processes that are listed in that to be given idea about the utility of the catalyst in the industry. Some industrial catalysis process will talk about it, and on the same cases for the difference between, you can say that process and catalysis that we have to talk about. So on the same case we'll go ahead. Difference between process and catalyst. Difference between process and catalyst here. In terms of process, that the Haber's process for the manufactures of ammonia like N2 plus 3H2, that will give 2NH3, and for the catalyst here, that finally divided iron and molybdenum as a promoter, and the conditions are that 200 bar pressures at 723 to 773 Kelvin temperature. Nowadays, a mixtures of iron oxide, potassium oxide and aluminum is used here. For the second difference for the process here, that it is your Oswald process for the manufactures of nitric acid like N4NH3 plus 5O2, it will give 4NO plus 6H2O. Another that they can have is 2NO plus O2, which will give 2NO2, and another 4NO2 plus 2H2O plus O2, that will give 4HNO3 here, that will in the form of aqueous. But in terms of catalyst here, that the platinized that asbestos temperature is 573 Kelvin. For the process here, this is the contact process for the manufactures of the sulfuric acid, which is 2SO2 plus O2, that will give 2SO3, SO3 plus H2SO4, that will give H2S2O, that is O7 here in the form of liquid, which is your known as oleum. And another is H2S2O7, that will form a product here, plus H2O in the liquid, so it will give you H2SO4 here in the form of aqueous. But for the catalysis here, that is your the platinized asbestos or the vanadium pentoxide, that is V2OO, that 5 we have. The temperature is 673 to 723 Kelvin here. On the same cases we'll go ahead, and that is your the questions that the fourth questions I will give you as an homework, which is your in the Haber's process, that the hydrogen is obtained by the reacting the methane with the stream in the presence of NiO as catalyst, and the process is known to be the stream reforming, and why is it necessary to remove CO when ammonia is obtained by the Haber's process as well. Another question is, why is the ester hydrolysis slows in the beginning and becomes the fastest after some time. And the other question is, what is the role of the desorptions in the process of catalyst as well. So these were the three questions I will give you as a homework that you have to solve by your side, so that it will be get to know that are you able to solve it out or not. Now we'll go ahead further, which we have to talk about it in terms of it, and that is also the another one, and that is also, even we can say that that is important here. The another topic we'll discuss about it, which is related to the colloids here. So colloids. So in terms of colloid here, that where solute is dispersed phase and solvent is your dispersion medium. So on the same cases for the colloid here, that we have learned in the unit 2 that the solutions are homogeneous system. That is the unit 2 we had discussed about the solutions there in the detail, and that is also known as the sand and water when stirred gives a suspension, and it slowly settles down with the time between the two extremes of suspensions that and solutions that we come across a large group of subsystem that called colliding dispersions or simply collide. A colloid is a heterogeneous systems in which one substance dispersed phase as very fine particles in another substance that called dispersion medium, where the essential difference between a solutions and a colloid is that of the particle size, and when in the solution that the constituent particles are that is in tons, that particles of a single macro molecule such as a protein or that synthesis polymer, or an aggregate of many atoms, ions and molecules as well, that collides. Particles are larger than a simple molecule, but are small enough to remain suspended, and their range is diameters between 1 and 1000 nm, that is 10 to the power 9 to 10 to the power 6 m here. So the colloidal particles that have enormous surface area per unit mass, and as a result of such their small size, you have to consider a cube with 1 centimeter side, and it has a total surface area of 6 centimeters square. I mean, if it were divided equally into 10 to the power 12 a cube, the cubes would be the size of the large colloidal particles and have a total surface area of 60,000 centimeters square or 6 meters square, where this enormous surface area leads to some special properties of colloidal that to be discussed later in this unit as well. Now we'll discuss about the classifications of colloids, and that is also an important one here. Classification of colloids that we have. So classifications of colloids, in terms of it, that the colloids are classified on the basis of their following criteria. That is, the first we have is your physical state of dispersed phase and dispersion medium. Second is the nature of the interaction between the dispersed phase and suspended medium. Another third is a type of particles of the dispersed phase that we have. So on the same cases, we will be going ahead, and that is the first we have the classification based on the physical state of the dispersed phase and the dispersion medium that we have to talk about it, and that even though which is important here. So on the same cases, we will be going ahead. The first we'll talk about it, and that is the classification based on physical state of dispersed phase and dispersion medium. In the same cases here, that depending upon whether the dispersed phase and the dispersion medium that are solid, liquid, or gases, and 8 types of colloidal systems that are possible. A gas mixed with another gas forms a homogeneous mixtures and hence is not a colloidal system, and that the examples of the various types of colloids along with their typical names that are listed here. So the types of colloidal system, we'll talk about it, where the dispersed phase, dispersion medium, type of colloid, and examples there are. So for that we'll talk about it, and here in the same cases we will talk about many familiar ones as well, but we'll go ahead with the table first. That is dispersed phase, then dispersion medium, types of colloid, and of course the examples. So dispersed phase we have here, which is that is your solid. Dispersion medium we have a solid. Type of colloid is solid solution. दोनों solid है तो solid solution बनेगा. Some colored glasses and gemstones. Okay. Now just another one we have here is that is your the solid and liquid. We'll talk about it, and in terms of it, solid, liquid, where that is will make a solution, which is the colloidal state. Okay, so in the same cases, the example for that we have when solid and liquid mix, so that is paints and cell fluid. Cell fluid as well that we have. Now we'll go ahead with the third category we have. So here we go ahead with another one that we have to talk about it, which is your the solid here. Then we have your gas. So that is we'll get here is your aerosol, and of course that is it will be the example is your smoke and dust that we have. In the same cases we have another one that is your kerosene, and that is your here it is your smoke and dust here. And after that we'll have another one which is your liquid and solid, that is your gel. So liquid and solid is gel, so that is cheese, butter and jellies. Then the next we have here is liquid, and that is your emulsion, and which is milk and hair cream. Now after liquid it is your liquid and gas. So the liquid and gas is your aerosol, and for that is your the fog, mist, cloud and insecticide. Yeah. Then insecticide sprays as well. Now we'll talk about the gas and liquid as well. For gas and liquid, so for gas and liquid that it forms a solid solution. And then that the example for this is your pumice stone, and foam, rubber. Then again in the last we have is your gas liquid. For the gas liquid it is your foam, so that is your froth, whipped cream, soap lather. The last we have is your gas, that is from homogeneous solution. Okay, so that we have to discuss here. After that, for as I told you here, many familiar commercial products and natural objects are collide, and that is, for example, that the whipped cream is a foam and which is a gas dispersed here, that is in liquid, and firefighting foams used at emergency airplane landing, that are also called collider systems. Most biological fluids are aqueous solutions, that is solid, also collider system. That most biological fluid are aqueous salts, which is your solid, disappeared in water. So that is within a typical cells, proteins and nucleic acid are colloidal sized particles that dispersed in an aqueous solutions of iron and the small molecules as well. Out of the various types of colloids here that we had discussed, so the most common are salts, which is solids and liquid, gels like liquid and solid, and take up the discussion of the sauce and the emulsions only. And further it may be mentioned that if the dispersions medium is water, that the sol is called the aquasol or the hydrosol, and if the dispersion medium is alcohol, it is called alcohol, and so on. So the next we'll talk about it, which we have to talk about here as well, which is the another one is the classification, that is based on nature of interaction between the dispersed phase and the dispersion medium here. which is classification based on nature of interaction between dispersed phase and dispersion medium. That we have to talk about it here. So LYO, that is the liquid that is philic, that is loving food, and for that phobic is your many, that is we have. So that we'll discuss here as well. On the same case, depending upon the nature of that is the interactions between the dispersed phase and the dispersion medium. So the colloidal salts are divided into the two categories, namely which is lyophilic, which is solvent attractive, and lyophobic, which is solvent repelling. And if the water is in the dispersion medium, that the term used for the hydrophilic and the hydrophobic. So we'll discuss lyophilic colloids and other lyophobic colloids as well. So the first we'll discuss here, which is your lyophilic. So in terms of lyophilic colloids here, it is that the word lyophilic means the liquid loving colloidal salts directly formed by mixing substances like gum, that is gelatin and starch, rubber, etc. with a suitable liquid like dispersed medium that are called lyophilic salts. And important characteristics of these salts as that is that of if the dispersion medium is separated from the dispersed phase, say by evaporation, that the salts can be reconstituted by simply that remixing with the dispersion medium. And that is why their salts are that is also called as reversible salts. Furthermore, these salts are quite stable and cannot be easily coagulated as distinguished later below. So for the second one we'll have is your lyophobic. In terms of lyophobic colloids, so in the that is we have to discuss here. So in terms of lyophobic that we talk about it, so here, and that is that the word lyophobic, that means here that is the liquid heating substances like metals, they have their sulfides, etc., and when simply mixed with the dispersion medium, that do not form the colloidal salt, and their colloidal salts that can be prepared only by the special method as to be discussed later. Such salts are called lyophobic salts, and these salts are readily precipitated or coagulated on the additions of the small amount of the electrolytes by heating or by shaking the hands, and that are not stable. Further, once precipitated, they do not give back to the colloidal salt by simple additions of the dispersion medium, and hence these salts are also called the irreversible salts. Lyophobic salts need stabilizing agent for their preservations as well, that we have to discuss here, and even though which is important as I told you. Now we'll go ahead further, which will discuss about the classification that is based on the types of particles of the dispersed phase, and multimolecular and macromolecular and associated colloids as well, that we have to discuss here, which is in the detailed as well. So let's go ahead to discuss for that, and which is the classification based on types of particles, that is classification based on type of particles of of the dispersed phase and multimolecular, macromolecular and associated colloids. So here that depending upon the type of the particle of the dispersed phase, the colloidals are classified as multimolecular, macromolecular and associated colloids as well. So first we'll discuss about it, and that is the multimolecular colloids here. Multimolecular colloids. So in terms of multimolecular colloids here, we are on dissolutions are large numbers of atoms or smaller molecules of a substance that aggregate together to form a species having size in the colloidal range, which is a diameter that is less than 1 nm, and that the species thus formed are called multimolecular colloids. For examples, a gold salt that may contain a particle of various sizes having a many atoms, and sulfur salts consist of particles containing 1,000 or more of S sulfur molecules as well. On the same cases, we'll talk about the second one, which is your macromolecular colloids. So in macromolecular colloids here, that that is your suitable solvent forms solutions in which the size of the macromolecular may be in the colloidal range, and such systems are called macromolecular colloid, and these colloids are quite stable and resembles the two solutions in many respects. Examples of naturally occurring macromolecules are starch, cellulose, protein and enzymes, and those of man-made macromolecules are polyethylene, nylon, polystyrene, synthetic rubber, etc. We'll talk about the third one, which is associated colloids. Associated colloid, which is Miscel. So this is in this that there are some substances which at low concentrated behave as normal strong electrolyte, but as higher concentration that exhibit the colloidal behavior due to the formations of aggregates, and the aggregated particles thus formed that the formations of aggregate, and the aggregated particles thus formed and are called Miscel. So these are also known as associated colloids, and the formations of Miscel take places only above a particular temperature that is called Kraft temperature, and above particular concentration that is called critical Miscel concentration, which is CMC. And on the dilution, these colloids revert back to individual ions and surface that active agents such as soaps and synthetic detergent that belonging to the class. For soap, the CMC is 10 to the power minus 4 to 10 to the power minus 3 mole liter inverse, and these colloids have both lyophobic and lyophilic parts, and Miscels are contained as many as 100 molecules or more as well. On the same cases, we'll discuss about the mechanism of Miscel formations that we have to discuss here, and even though which is also important for the same, and on the same behalf of it we will be going ahead to discuss, and that is your mechanism of Miscel formation. Mechanism of Miscel formation. So here on the same cases, here we have to discuss. Let us take an example of soap solution, where soap is sodium or potassium salt of higher fatty acids and may be represented by RCOO minus Na. An example is sodium stearate like CH3, CH2, 6, the COO minus Na plus, which is a major component of many bar soaps, and when dissolved in water it dissociates into the Na plus ions, and where aceto double O minus ions as well. And how it is consists of the two parts, where that is a long hydrocarbon chain R, and also called a non-polar sail, and of course which is the hydro phobic water repelling, and polar group which is COO minus and also called polar ionic, and that is your head, and which is the lyophilic water loving here. So that will make it here only, so that you will get to know about it. On the same cases, this has been CH3, CH2, then again CH2, 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 CH2. That we have number of three, that we have 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 we have. So that is your 1 2 3 4 5 6 7 8 9 10 11. Then we have 12 13 14 15 16 that we have. Then again we have here, for after that it will be belonging to carbon up, and then it is your O minus Na plus that we have. So this is from here till the last. This is your sodium stearate, which is the formula we have C17H35 COO minus Na plus here that we have. So when dissolves in water, Na plus removed, so that we'll find it out for that as well, and eventually we have to find it out here. For the same case, the same will do for the hydrophobic tail for the stearate ions we have. So that is also will have as follows. I will just make it here from here. CH3, CH2, 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 CH2. It is 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 and 16. Then we have your C bond O, and that is O minus. So this is what we have as your hydrophilic head, and this is from here to this is your hydrophobic tail, which is your stearate ion. Now for the another one we have, we'll talk about it. This is the hydrophobic head, and this is hydrophobic tail. So this is the hydrophobic and hydrophilic part of stearate ions here as well, and that is now we'll go ahead for to find it out for the solution for the arrangement of the stearate ions on the surface of water at low concentration of soap as well. So for that, it is represented like this. This is a beaker where there is a water, then here it is stearate ions. Okay, So yes, this is your stearate ions here that we have to talk about. This is the arrangement, as I told you, for the RCOO minus ions that are therefore present at the surface with their COO minus groups in water, and that hydrocarbon change are staying away from it and that remain at the surface, but at critical Miscel concentration that anions are pulled into the bulk of the solutions and aggregate to form a spherical shape with their hydrocarbon chains that pointing towards the center, and the spheres with COO minus part remaining outward on the surfaces of the sphere. An aggregate thus formed is known as ionic Miscel, and their Miscels have that contained as many as 100 such ions as well. For that, this that examples of the, that is your lauryl sulfate, which is CH3CH2 11, the whole 11, that is SO4 minus, and Na2 plus as well, where that in the same cases the polar group is your minus SO4 minus, and along with that long hydrocarbon chain, and hence the mechanism of Miscel formations here also is the same that of the soap here. So will be forming in the form of like this. This is being like, so it is like 2 3 4 5 6 7 8 9 10. Okay, so this is your COO minus, then we have COO minus, then COO minus. This is your ionic Miscel, which is your COO minus, COO minus, COO minus, COO minus, COO minus, then we have COO minus and COO minus we have. So this is the forming here. This is the hydrocarbon parts that we have, and on the same cases, so that we have, now we'll discuss about the cleaning action of soap that we have discussed here. That is cleaning action of soap that we have to discuss. Here it has been mentioned earlier that the Miscel consists of hydrophobic and hydrocarbons like central core here, and on the same cases the cleaning actions of soap is due to the fact that the soap molecules form Miscel around the oil dropped in such a way that the hydrophobic part of the stearate ions is in the oil droplet, and hydrophilic part projects out to the grease droplet like the Bristol, and that sends the polar group that can interact with water, and that the oil droplet surrounded by the stearate ion is now put into the water and removed from the dirty surfaces. So thus the soaps helps to the emulsions and washing away of oils and fats, and the negatively charged that we have sheet around the globus prevents that the form coming together, the forming the aggregates as well. So on the same cases here, the structure we have, this is a grease on cloths, then this is your the stearate ions arranging around the like grease droplets. The another we have, this is your grease droplet surrounded by the stearate ion, which is your Miscel formed here. So here we will be ending it up, and first of all it's a huge request from my side to all the viewers to please go through with the subscribe button, and please like, share and subscribe our channel so that many and maximum people can get the information at once, and even though you can also enjoy the video as well. And other than that, chemistry we had completed your software engineering, and your that is your software engineering, and your of course that is we had done sociology. lastly. And other than that, we are dealing with the quantitative aptitude, where we had started with arithmetical ability. We had completed operations on numbers and LCM and SCM of numbers. Then we had done your which is decimal fractions, and of course we had done your that is simplification, and we had started with another topic is your we had completed square roots and cube roots, and as well as we had done your the averages we had started with. And after that, we are dealing with the reasoning, where we had completed the verbal reasoning, which is consist of general mental ability and the logic reasoning. And in non-verbal reasoning, we had started with, and which we had completed your series, analogy, classification, analytical reasoning, mirror image, water image, embedded figure, completions of incomplete pattern as well, which we had end up with. And next we'll start discussing about the figure pattern as well, the figure matrix, we can say that. After that, in terms of chemistry, we're talking about, we had completed unit 1, which is the solid state, where we had completed the general characteristics of solid state, amorphous and crystalline solid, classification of crystalline solid, crystal lattice and unit cell, number of atoms in unit cell, closed packed structure, packing efficiency, calculation involving the unit cell dimensions, and imperfections in solid, electrical properties and magnetic properties as well. In the terms of unit 2, which we had covered up the types of solution, expressing the concentration of solution, solubility, vapor pressures and liquid solutions, ideal and non-ideal solution, colligative properties and determination of molar masses, abnormal molar masses as well. In unit 3, which we had covered up is your electrochemistry, where electrochemical cells, galvanic cell, Nernst equation, conductance of electrolytic cells and electrolysis, batteries, fuel cells and corrosion. Unit 4 is your chemical battery kinetics, we had completed, that is your rate of chemical reaction, factors influencing the rate of reaction, integrated rate equation, pseudo first order reaction, temperature dependence on the rate of reaction, collisions, theories of the chemical reaction as well. Unit 5, which we had started, surface chemistry, which we had covered up the adsorption, catalyst, collide, classification of collide, emulsions and collide around us. There is some topics that we have to cover up here. After completing that, we'll start discussing about unit 6, which is your general principles and process of isolation of elements, that is the occurrence of metals, concentrations of ore, extractions of crude metal or concentrated ore, thermodynamic principle of metallurgy, electrochemical principle of metallurgy, oxidation reduction, refining, uses of aluminium, copper, zinc and iron. Then the next unit, which is your unit 7, the P block element, which we have to cover up group 15 element, dinitrogen, ammonia, oxides of nitrogen, nitric acid, phosphorus, allotropic forms, phosphine, phosphorus halides, oxo acids of phosphorus, group 16 element, dioxygen, simple oxides, ozone, sulfur, allotropic forms, sulfur dioxide, oxo acids of sulfur, sulfuric acid, group 17 element, chlorine, hydrogen, chlorine, chloride, oxo acids of halogens, interhalogen compound, group 18 elements. Then unit 8, the D and F block element, where we have to cover up the position in the periodic table, electronic configuration of the D block element, general properties of the transition element of D block, some properties of the some important compounds of the transition element, the lanthanides, actinides, and some application of D and F block elements. Group 9, unit 9, which we have to cover up coordination compound, Warner's theory of the coordination compound, definition of some important terms pertaining to the coordination compound, nomenclature of coordination compound, isomerism of the coordination compound, bonding in the coordination compound, bonding in the metal carbonylysis, stability of the coordination compound, importance and application of the coordination compound here. So we will end up with, thank you, hope you enjoyed this video. If you like this video, please give a thumbs up and give a suggestion in the comment box. Thank you.